Stephen, what's 3 plus 4? Yeah, 7 works. 7 works. Katie, what's 3 plus 4? Oh, it could be 1 if it's 4 plus negative 3. Sure, it could be 1. Okay, you're adding vectors. You're doing the tough grade 6 math now. Stephen did the easy grade 1 math, right? Kenway, what's 3 plus 4? Could be 7, but could be 1, could be negative 1, could be 5, could be any one of a number of things, actually. On Thursday of last week, we learned that in grade 1, you could add scalars. 3 plus 4 was equal to 7 every single time in grade 1. In grade 6 or grade 7, you learned to add vectors, but you learned to add them in one dimension. In other words, 3 to the north, 4 to the south. 3 to the south, 4 to the north. You might not have thought of it as adding vectors together. You might not have called it adding vectors, but in essence, that's what you were doing when you were adding positives to negatives. Now in grade 11, you're learning to add vectors together that aren't in one dimension. We don't have 3 to the north and 4 to the south. We have 3 to the north and 4 to the west. If that's the case, then the sum of 3 plus 4 might equal 5. Or it might equal something else entirely, depending upon what direction the 3 and the 4 are in. We said when we're adding vectors in 2 dimensions, the goal is to always get a right-angled triangle. Okay, get a right-angled triangle, always. Once we have a right-angled triangle, then we can use some fairly simple math, namely the Pythagorean theorem, a squared plus b squared equals c squared, and a little bit of trigonometry, but thankfully, notice, some not too difficult trigonometry to find what the angle is, which is important because when we're adding vectors together, we get a vector that has a direction. Here's the rules of vector addition so that we can get that ultimate goal of a right-angled triangle. Okay, number 1, you got to draw vectors. Your vectors are line segments with arrows on the end of them. We're drawn roughly to scale, as much as we can to scale. So in other words, if we were adding 3 to the north and 4 to the west, the 3 would look like this maybe, and the 4 might look something like this, a little bit longer than the 3. Okay, I didn't measure those. I don't know if it's perfectly proportional to each other, okay, but in the end, it's roughly to scale. Next thing we got to remember is to draw them front to back. This is the back of a vector. This is the front. This is the back. This is the front. So we can draw it in one of 2 ways. We can draw it either like this, with a 3 like this, drawn front to back. Or we could have drawn it like this, with the 4 drawn first, drawn front to back right here. In either case, the resultant vector, which is the sum of the vectors, right? When you add vectors together, you get the sum. 3 plus 4 is 7. The sum is 7 in scalars. Here, 3 plus 4 is equal to this, or 3 plus 4 is equal to this. That red resultant vector has to be drawn from start to finish. Back to back, front to front, back to back, front to front, from start to finish. This red vector, this red resultant vector, completes the right-angled triangle that was the ultimate goal, right? Now we can find its value by using the Pythagorean theorem. So, how do we go about doing that? So in both cases here, we'll call it C, right, the hypotenuse. We'd say C squared is equal to a squared plus b squared, or C is equal to the square root of a squared plus b squared. So we'd say C is equal to 3 squared plus 4 squared. Do the math there, it works out to be 5. Now that's the magnitude of the sum of the vectors, 5. But we got to find the direction as well. The direction is measured by an angle, always at the start of your vector diagram. In this case, the angle is going to be the inverse tan function, the second function tan of opposite over adjacent. You guys remember those trig functions, SOHCAHTOA? I learned them when I was in high school or junior high, whenever I learned them. Not SOHCAHTOA, actually. My math teacher taught me, I remember, Oscar had a heap of apples. Okay? OH, AH, OA. It's still SOHCAHTOA, right? Just a little different mnemonic device to help me remember. You guys ever heard that one? No? Okay, SOHCAHTOA it is. TOA, tan, opposite over adjacent. The inverse tan of 4 over 3. What's that going to give me? We're trying to find the angle here. It's not going to work out to be 5. Let's pull out the calculator and figure that out. Here's the keystrokes we'd go through to figure that out. Second function, tan. Okay, it's not tan, it's second function tan. Okay, if you use the tan function without the second function, you must already have the angle. We don't. So we got to use second function tan. 4 over 3 gives us 53.1 degrees. Now, if you do it the other way, with the other angle, we'd say theta is equal to the inverse tan of opposite over adjacent, which is 3 over 4. Let's try that one. The inverse tan, second function tan of 3 divided by 4 gives me 36.9. What do you notice about 53.1 and 36.9? What do you notice about those two vectors? Those two angles, I should say. Yeah. Yeah, they add up to 90, and that'll happen every single time. Every single time. So what's our answer here? We could say 5 at 53.1 degrees, or we could say 5 at 36.9 degrees. How can it be either one? It depends upon where we measure from. But when we're measuring something, the second, third day of physics, we're measuring a position. We measured it from something, right? We have to measure the angle from something as well. From what? 53 degrees from what? 36 degrees from what? This would be 53 degrees, listen carefully, 53 degrees west of north. This would be 36.9 degrees north of west. Where does that come from? Well, the angle here in this one is measured from the north axis. See that? The angle here is measured from the west axis. So this is measured west from north. Okay? It's going west from the north. This one is measured from the west, but it goes north from the west. So it's going to be north from west or north of west. Does that make a little bit of sense? So we could say now 5 meters, whatever it is, at 53 degrees west of north. Perfectly correct answer. Or 5 at 36.9 degrees north of west. Also perfectly correct answer. Well, it depends upon whether we're adding velocity or displacement or force or momentum or any other vector. So I don't have units there because I didn't give you units in the question. Okay. All right. We worked on a couple questions on Thursday involving two vectors, and I think we managed to do those, right? Okay, in the end, we didn't need to draw a vector diagram for either of these ones because they were both on the same axis. For this one, it would have been 10 meters north and 20 meters east. This one would have been 10 meters to the west and then 20 meters to the south. The resultant vector would have been here. The resultant vector would have been here. This angle, I don't know what the value is, but this value of theta would have been something degrees east of north, because it's measured from the north axis, but east of north. This one would have been something south of west, measured from the west, but south of west. Right? Hey, in both of those problems that we did on Thursday, and in the example we just did a minute ago, we had two vectors that we had to add together. We automatically got the ultimate goal, which was the right-angled triangle. What if we have three vectors? What if we have a situation like this, where we have 25 meters to the north, 20 meters to the east, and then 30 meters to the north? Well, we still have to draw a vector diagram following the same rules, but the ultimate goal isn't met right away. We don't get a right-angled triangle right away. Let me show you. 25 meters to the north is going to look something like this. Then we got 20 meters to the east. It's going to look something like this. Then we have 30 meters to the north. The resultant vector would still be drawn start to finish like this, but that's not a right-angled triangle. It's not even a triangle, let alone a right-angled triangle. So what do we got to do? You can see the sentence that I've got listed up here. It says, must use vector components when we're adding these together. Follow along with me, and then you can write it down, okay? We get two more examples for you to work through yourself, so just follow along right now. Components, x and y. This is x. Everything on this axis is x, and everything on this axis is y. Let's add up each of these vectors on each axis. So, how much of this 25 is on the x-axis? How much of this is on this axis? 0. Good. How much of this is on this axis? 25. Let's look at the 20 now, the second vector. How much of that 20 is on the x-axis? 20. How much of that 20 is on the y-axis? 0. That making sense so far? Yeah. All right, what about the third one? 30 meters. How much of that is on the x-axis? None. How much is on the y-axis? Now, let's add these up. I get 0 plus 20 plus 0 is 20 meters. 25 plus 0 plus 30 is 55 meters. Now comes the kind of the crux of it, right? 20 meters to the, which way is that? East. Look, it's the x-axis, and it's positive, so it's going to be 20 meters to the east. 55 meters to the, it's on the y-axis, and it's positive, so it's going to be to the north, right? We're going to draw a resultant vector from start to finish. Take a look at that resultant vector for a second. Internalize it. Remember what it looks like. Let's scroll up. What about that resultant vector? Doesn't it look the same? It's not a coincidence. What we've just done, though, is created that resultant vector in, what's our goal? A right-angled triangle. Now we got a right-angled triangle. What do we do with this? What do we do with this? Same thing we did with our other problems, right? We get the hypotenuse, c, and we get the angle, theta. C would be equal to the square root of 20 plus 55 squared. And theta would be the inverse tan function of opposite over adjacent, 55 over 20. Does that kind of make sense? So let's go back to that first page of notes with this. Remember the goal. The goal is to always get a right-angled triangle. In this question, we had one right away. In this question, we had one right away. In this question, we had one right away. In this question, we didn't. We had some funny shape. I don't even know what you call that. So what do? We wanted to turn it into a right-angled triangle. How do we do that? Break it into its x and y components. Figure out how much of each of them is on x and y. Get a total x and y. And then from that, get yourself a right-angled triangle. Got it? Let's get this angle here, okay? Let's figure out what that is. And so we can express it, something of something. We're going to say it's the inverse tan, second function tan of 55 over 20. We get an angle here of 70 degrees. 70 degrees, what's it going to be? West, east, north, south, west of south, south of south, north of south? What What's it going to be? Where are we measuring the angle from? This is our axis, right? Which axis are we measuring the angle from? Is that east, south, north, west? Cody? East. Okay, so it's going to be something of east then, right? Okay. Where is it going from the east? Good. It's going north from the east, north above the east. So we're going to say north of east. Okay. We got a few minutes left in class. Here's what I want you to do for the remainder of class and for homework tonight, if you don't finish it in class here. Simply add these together. Don't just say 10 plus 15 plus 12 plus 20 is, okay, whatever they are, adding scalars. Okay. Draw the vector diagram. It's going to be an ugly looking vector diagram because you're going to have 4 vectors plus the resultant. But then from that, break it into x's and y's and get a right angle triangle and then do what we always do for the right angle triangle.